Have you ever stopped to think about the incredible, invisible world of forces that's active all around us all the time? From the very chair you're sitting on to the tallest skyscraper, everything is under constant stress. It's being pushed and pulled by forces we can't even see. So today, we're going to pull back the curtain on this hidden world and really get into the science of mechanical stress.
Okay, so this sounds like the beginning of a really weird joke, right? You've got a piece of high-tech medical equipment, a massive underground tunnel, and this super precise, tiny little gear you'd find in a robot. What could they possibly have in common?
And there's the answer. Every single one of them is engineered to survive an unbelievable amount of mechanical stress and environmental pressure. They are locked in a constant, invisible fight for survival. So, let's break down exactly what they're up against.
All right, let's start with the absolute fundamentals. Before things start moving or shaking, an object just sitting there is usually dealing with two very basic forces, a push and a pull.
Think about it this way. Compression is a squeezing force. It's what happens when you push down on a spring, trying to make it smaller. Tension is the complete opposite. It's a stretching force, like when you pull on a rubber band. It's amazing, really, that these two simple ideas are the building blocks for just about every complex structure in our world.
And compression is just everywhere. It's the mind-boggling weight of the Earth, pressing down on those rock pillars deep inside a mine. It's the squeezing force on tunnel walls as they're being dug out. And it even happens on a tiny scale, like the pressure a medical implant puts on the very bone it's screwed into.
Then, of course, you've got tension. This is the force engineers are measuring when they test exactly how much it takes to yank an anchor bolt out of concrete. It's also that stretching stress that happens on the bottom of a beam when you bend it. And in really extreme cases, it's what a steel plate goes through a millisecond before something punches right through it.
But let's be real. The world isn't static, is it? Things move, they shake, they collide. And that brings us to a whole different class of forces, dynamic loads. And this is where things get really intense.
So a dynamic load isn't some nice, steady push or pull. No, it's a force that changes, and often it changes fast. We're talking about sudden impacts, constant vibrations, or a stress that repeats itself over and over and over again. Honestly, these are usually the culprits when things break unexpectedly. Just think about the raw, shaking power of an earthquake. That right there is seismic loading, a massive, unpredictable dynamic force that engineers have to account for when they design our buildings and bridges. Or you could have something a lot more predictable, but just as destructive over time, cyclic loading. This is that repetitive, back-and-forth stress on a joint in a robot or engine, repeating millions, maybe billions of times, slowly wearing it down.
And then there are vibrations. Get this. In some of these research tests, materials are subjected to vibrations at 100 hertz. That's 100 cycles every single second. Can you imagine that kind of high-frequency stress just shaking a component apart from the inside?
And finally, you have the pure, brutal force of a sudden impact. Some of these experiments involve smashing things at 18 meters per second. That's over 40 miles per hour. It's all about understanding what happens to materials under those extreme, instantaneous loads.
So, we've got static forces, the pushes and pulls. We've got dynamic forces, the shakes and impacts. But you know what? There's a third major player here that we can't ignore, the environment itself. Nature has its own ways of applying stress, and trust me, they are relentless.
Yeah, nature has a whole toolkit for destruction. First up, thermal stress. This can be anything from a sudden 20-degree temperature drop that cracks solid granite to heating sandstone up to 1,000 degrees Celsius. Then you've got chemical attacks, like acidic water eating away at coal seams. And don't forget hydrological forces, that incredibly powerful freeze-thaw cycle, where water gets into tiny cracks, freezes, expands, and literally tears rocks apart from the inside out.
So here's the most important thing to remember. In the real world, these forces almost never happen one at a time. The true challenge, the real-world problem for engineers, is figuring out how they all combine and interact simultaneously. To really see how complicated this gets, picture the floor of a deep mine. Okay, so first, it's already under this incredible in-situ stress, just from the weight of all the rock around it. Then, on top of that, the mining process itself introduces a whole new set of stresses. And if that wasn't enough, what if there's a body of water, an aquifer, trapped below? Well, now you've got that pushing up with immense pressure. See? All three forces are happening at once. And here's another perfect example. If you want to build a bridge that lasts in a permafrost region, you can't just think about the dynamic force of an earthquake.
You absolutely have to factor in the environmental stress from the ground freezing and thawing. The forces are interconnected, and if you ignore one, you're just asking for a catastrophic failure.
So why do we go through all this trouble? Why do we spend so much time measuring and modeling all these invisible forces? Well, because understanding them isn't just an academic exercise. It's absolutely critical to our safety and to our ability to build a better future.
And the payoff is massive. This research leads to safer buildings that don't collapse in earthquakes. It means we get medical implants that last longer and are far more reliable. It lets us build machinery where we can predict when a part might fail from vibration. It helps prevent deadly rock bursts in mines and tunnels. At the end of the day, it makes our entire world safer, more efficient, and more reliable.
So I want you to just take a look around you. The walls of your room, the street outside your window, the phone in your hand, they are all fighting a constant, silent battle against compression, tension, vibration, and a whole host of other forces. It makes you wonder, doesn't it? What invisible battle is happening right next to you?